Walk down any quiet street, and if you listen closely, near a utility pole, you might hear a low, steady hum coming from the transformer. Even if it is completely idle and not actively powering a single house, that metal cylinder is still vibrating, and it is still radiating heat. This physical reality contradicts the ideal theory we learn on paper. According to magnetic Ohm's law, electrical current politely and perfectly pushes magnetic flux through a core with zero friction. But if you build a physical machine based strictly on those pristine equations, it will run terribly and quickly overheat. Real physical materials possess geometric quirks, hard capacity limits, and physical memories. They shatter our perfect equations, forcing engineers to design around the messy reality of physical metals. The first way reality breaks our math happens in physical space, specifically when magnetic flux runs out of steel and is forced to cross an open air gap. This diagram of a ferromagnetic core highlights a very narrow 0.05 centimeter air gap. The ideal math assumes the magnetic flux lines will march straight across that gap, keeping the exact same cross-sectional area as the steel they just left. But air has high reluctance. It naturally resists magnetic fields. So to find an easier path to the other side, the flux lines repel each other and bulge outward at the edges, exactly like water spraying out of a pinched hose. By spreading out into the surrounding air, that outward bulge physically increases the total cross-sectional area of the gap. Engineers call this phenomenon fringing. Because a wider path means less resistance, fringing actually drops the gap's overall reluctance. If designers don't multiply their math by a specific fringing factor, their calculations for the whole circuit will overstate the resistance and ruin the design. The second problem is a hard physical capacity limit inside the core material itself. On a whiteboard, you can pump infinitely more current into a wire coil, and the math says you will endlessly generate proportionally more magnetic flux. Inside the steel, magnetic fields are created by microscopic crystalline structures called domains. As you increase the electrical current, you are aggressively snapping more and more of these chaotic, randomized domains into rigid alignment. This graph, known as a magnetization curve, plots that flux density against the driving current. The line rises steeply at first, but eventually you run out of unaligned domains. The line abruptly flattens out into what we call the saturation knee. For common silicon steel, that physical limit hits around 1.5 to 1.8 Tesla. Push the material past that saturation point, and the magnetic flux barely increases. You are simply wasting electrical current, converting it directly into excess heat. The final issue is that steel has a physical memory, and it reacts very poorly to changes over time. In a perfect model, the moment you turn off the power, the magnetic field in the core drops instantly to zero. In reality, those microscopic domains we just aligned refuse to fully randomize when the current stops. They lock into place, effectively turning the iron core into a permanent magnet. This diagram traces that physical memory, showing how the magnetization curve takes a completely different path on the way down than it did on the way up. To operate a machine on alternating current, you have to reverse the magnetic field entirely. That forces the machine to expend energy just to break the domains out of their locked alignment. This lag is called hysteresis. The physical area trapped inside that divergent loop represents pure energy permanently lost to heat. And this isn't a one-time penalty. That loop of wasted heat happens during every single cycle of alternating current, 50 to 60 times every second. Hysteresis, working in tandem with internal electrical friction known as eddy currents, completely explains our mystery from the beginning. It is exactly why a utility transformer runs hot and hums all day, even when it is doing absolutely zero mechanical work. These microscopic quirks we have discussed scale up into massive industrial consequences. True engineering is the art of respecting material limits. We slice steel into thin laminated sheets to fight core loss, and we carefully balance the entire machine to operate just millimeters below that saturation knee. Now that we understand how flux actually misbehaves inside a physical core, the next step is figuring out how to extract usable power from it. To do that, we have to put that magnetic field in motion. Next time, we'll look at how changing flux creates voltage and dive into the mechanics of Faraday's and Lenz's laws.